Hello and welcome to Science Aura. I am Dr. Sachi Vale. For over a century, humanity's journey into the cosmos has been held hostage by a single, uncompromising mathematical law, the Tsiolkovsky Rocket Equation. To escape Earth's deep gravity, well, a rocket must burn fuel. But that fuel has mass, which requires more fuel to lift, creating an exponential penalty that limits our reach. Today we explore how SpaceX plans to break this cosmic bottleneck forever. To understand the scale of the challenge, look at the Saturn V. It was a mechanical titan, standing over 110 meters tall. Yet, of its colossal 3,000-ton launch mass, a staggering 92% was nothing but propellant. The actual payload delivered to the moon was a mere fraction of a percent. This is the tyranny of the rocket equation. We build towering skyscrapers of metal just to throw away almost all of it in minutes. Because of this mathematical reality, deep space missions have always been severely payload constrained. Robotic rovers sent to Mars are stripped of every non-essential gram, forcing scientists to make painful compromises. If we want to send humans to Mars, along with the life support systems, habitats, and heavy machinery required to survive, we cannot rely on traditional single-launch architectures. We need a fundamental paradigm shift. The solution SpaceX is pursuing is as elegant as it is daring. Refuel the spacecraft in orbit. Imagine driving your car across a vast, barren desert. If you had to carry all the gasoline for the entire round trip from the start, your car would need to be the size of a semi-truck. But if you can stop at a gas station along the way, your vehicle remains small, efficient, and highly capable. In space, low Earth orbit is that crucial pit stop. At the heart of this strategy is SpaceX's Starship, a fully reusable two-stage transportation system. The Super Heavy booster launches Starship into low Earth orbit, consuming nearly all its fuel to do so. Once in orbit, Starship is essentially empty, left with barely enough propellant to return home, let alone travel to Mars. This is where the Orbital Refueling tanker variant comes into play, launching repeatedly to fill the Explorer's tanks. To fully refuel a single Mars-bound Starship, SpaceX will need to launch multiple tanker flights. Each tanker carries a fresh load of liquid methane and liquid oxygen, docking directly with the waiting ship in orbit. Over several successive transfers, the Explorer ship's massive propellant tanks are completely replenished. When it finally leaves Earth's orbit, it does so with a full load of fuel, effectively resetting the rocket equation. By starting its deep space journey from orbit with a completely full tank, Starship can carry over 100 metric tons of useful payload all the way to the surface of Mars or the Moon. This is an order of magnitude increase compared to any rocket that has ever flown before. But executing this concept requires solving some of the most complex engineering and physics challenges in the history of spaceflight. The first and perhaps most daunting challenge is the behavior of liquids in microgravity. On Earth, gravity is our constant ally, pulling fuel down to the bottom of the tank directly into the engine's intake pumps. But in the free fall of orbit, gravity effectively disappears. Without a downward force, liquids do not behave like liquids anymore. They become chaotic, drifting, and unpredictable hazards. In microgravity, the dominant forces governing fluids are surface tension and cohesion. Instead of settling in a neat pool, the cryogenic propellant clings to the tank walls, crawls up structural ribs, or disperses into thousands of floating bubbles. This is a nightmare for rocket engines, which require a continuous, high-pressure, bubble-free stream of liquid fuel to operate safely and avoid catastrophic engine failure. If a rocket engine's turbopump sucks in even a small pocket of gas instead of liquid propellant, it can lead to a condition known as engine cavitation or dry running. The pump, spinning at tens of thousands of revolutions per minute, will suddenly overspeed, causing extreme mechanical stress, thermal spikes, and ultimately, an explosive destruction of the engine. Keeping the liquid at the drain is critical. In rocketry, the empty space above the liquid fuel in a tank is called the ullage. On Earth, the ullage gas naturally stays at the top. In orbit, however, the ullage gas and the liquid fuel mix into a chaotic slurry. To transfer fuel from one ship to another, or to restart the engines, we must find a way to separate this gas from the liquid and force the fuel back down to the outlet valves. SpaceX's primary weapon against microgravity chaos is microacceleration. By applying a tiny, constant forward thrust to the spacecraft, they can simulate a weak gravitational field. This gentle push forces the liquid propellant to slide along the walls and pool gracefully at the bottom of the tank, right where the transfer pumps and engine intakes are located. It is a simple concept with profound execution challenges. To achieve this settling, Starship utilizes its hot gas reaction control thrusters or its main Raptor engines in a low thrust mode. The acceleration required is incredibly small, often just a fraction of a milligee. Yet, maintaining this precise thrust over the duration of a fuel transfer requires highly sophisticated guidance and control software to ensure the vehicles do not drift off course or waste precious attitude control fuel. Even with microacceleration, moving hundreds of tons of liquid creates massive kinetic energy. As the fuel moves, it sloshes back and forth against the tank walls, creating forces that can easily destabilize the spacecraft's orientation. Controlling this fluid slosh requires complex internal tank structures, known as baffles, designed to absorb the kinetic energy and damp the liquid's motion. In addition to thruster settling, engineers use specialized internal hardware known as Propellant Management Devices, or PMDs. These devices exploit surface tension using fine metallic meshes, sponges, and galleries to trap and guide liquid fuel directly to the outlet, even when the bulk of the liquid is floating freely. They act like high-tech sponges, holding onto the liquid while letting gas escape. Once the fuel is settled, we face an even more relentless enemy: thermodynamics. Starship uses subcooled liquid methane and liquid oxygen. Methane must be kept at minus 161 degrees Celsius, and oxygen even colder at minus 183 degrees. In the harsh environment of space, maintaining these ultra-low temperatures is a monumental engineering feat. Space is not just cold, it is a vacuum, which means there is no air to conduct heat. However, heat from the sun, reflected light from the Earth, and the warmth of the spacecraft's own systems can quickly warm the cryogenic tanks. When these liquids warm up, they boil and turn back into gas. This process, known as boil-off, represents a constant loss of precious fuel that must be prevented at all costs. Aimed to combat boil-off, SpaceX employs advanced passive thermal control strategies. The first line of defense is Starship's polished stainless steel skin, which naturally reflects a significant portion of solar radiation. Additionally, when parked in orbit, the spacecraft can orient itself in a barbecue roll, slowly rotating to distribute solar heating evenly and prevent one side from baking in the sun. Underneath the steel skin lies high-performance multi-layer insulation, or MLI, consisting of dozens of ultra-thin, reflective plastic sheets separated by fine netting. MLI acts as a highly effective radiation shield in a vacuum. It prevents thermal energy from radiating inward toward the cryogenic tanks, keeping the liquid methane and oxygen stable for days or even weeks at a time. For long-term storage, such as orbital depots waiting months for Mars transfer windows, passive insulation is not enough. SpaceX must implement active cryocooling systems. These are essentially space-grade refrigerators that compress, cool, and expand helium gas to absorb heat from the propellant tanks and radiate it out into deep space, keeping the fuel subcooled indefinitely. Before any fuel can flow, the two massive spacecraft must find each other, align, and dock with millimeter precision. This is not a gentle docking like those seen at the International Space Station. We are talking about two vehicles, each weighing over 100 tons, joining together tail to tail. The docking mechanism must be incredibly robust to handle the structural loads of physical connection. The actual fluid transfer occurs through highly specialized connectors known as quick disconnects, or QDs. These umbilical interfaces must seal perfectly to prevent any leakage of highly flammable methane or oxygen into space. They must also be capable of rapid, reliable disconnection in an emergency, sealing both sides instantly to prevent explosive decompression or fuel loss. SpaceX chose a tail-to-tail configuration for Starship docking. This design simplifies the plumbing, as the propellant lines are already concentrated near the aft section close to the Raptor engines. By docking tail-to-tail, the ships can share the same structural mounting points used during launch, minimizing the need for heavy, redundant docking structures along the sides of the ship. Once docked and the lines are chilled down to prevent thermal shock, the actual transfer begins. But you cannot simply turn on a pump and push liquid into a sealed tank. You must manage the pressure. As liquid enters the receiver tank, the gas inside must be vented or compressed. If the pressure rises too high, the transfer will stall or worse, rupture the tank. To manage this, SpaceX uses a process called ullage recondensation. By spraying subcooled liquid into the receiver tank's gas head, they can cause the ullage gas to condense back into a liquid state, rapidly dropping the pressure without needing to vent precious gas into space. This closed-loop system ensures maximum efficiency, retaining every gram of propellant. In addition to thruster settling, engineers have proposed using centrifugal force to assist with fuel transfer. By gently rotating the docked spacecraft pair around a common center of mass, artificial gravity is created. This forces the liquid to the outer ends of the combined vehicle, naturally separating the gas and liquid and creating a reliable pressure gradient to drive the transfer. If pumps are used, they must be specially designed to handle cryogenic fluids. Cryogenic pumps operate under extreme thermal stress, shrinking and contracting as they are chilled. Any friction inside the pump can generate localized heat, causing the liquid methane or oxygen to vaporize instantly, destroying the pump's efficiency and potentially leading to catastrophic mechanical failure. To make this system practical, SpaceX plans to deploy specialized Starship variants known as orbital propellant depots. These are essentially giant, heavily insulated thermos flasks in space. Instead of transferring fuel directly from tanker to explorer, tankers will continuously feed the depot, which remains in orbit, ready to quickly top off departing starships in a single, rapid docking event. The orbital depot will feature a deployable sun shield, a massive, multi-layered umbrella made of reflective cap tin. This shield blocks the intense radiation of the sun, keeping the entire depot in permanent shadow. By reducing the thermal load to almost zero, the depot can store hundreds of tons of liquid methane and oxygen for months without experiencing any significant boil-off. The success of this orbital refueling architecture depends entirely on launch cadence. To fill a single depot in a reasonable time frame, SpaceX must achieve an unprecedented rate of launches. We are talking about multiple Starship launches per week, or even per day. This requires a level of operational reusability and rapid turnaround never before seen in the aerospace industry. If the booster and ship were not fully reusable, this refueling strategy would be economically impossible. Launching 10 expendable rockets to fuel one Mars mission would cost billions of dollars. But with Starship designed to fly, land, refuel, and fly again within hours, the marginal cost of each refueling flight drops to just the price of the propellant, making deep space travel affordable. SpaceX's choice of liquid methane as fuel, rather than liquid hydrogen, is a critical part of the refueling equation. Methane is far denser than hydrogen, meaning the tanks can be smaller and lighter. It is also much easier to store, boiling at a much higher temperature. Most importantly, methane can be manufactured directly on the surface of Mars using local resources. On Mars, carbon dioxide from the thin atmosphere can be combined with water ice mined from the soil through a chemical process called the Sabatier reaction. Powered by solar or nuclear energy, this mixture is converted into pure methane and oxygen. This means the return journey from Mars does not require carrying fuel all the way from Earth. We can manufacture it on site. By producing fuel on Mars, the return spacecraft can refuel itself on the Martian surface. It then launches back into space, using Mars's lower gravity to return to Earth without needing orbital refueling on the way back. This completes a highly efficient, sustainable, and repeatable logistics loop that connects our two worlds for the first time in history. To understand the power of this approach, compare it to other planned architectures, like NASA's Lunar Gateway. While the Gateway provides a permanent orbital station around the moon, it still requires incredibly complex single-use launch vehicles to deliver small payloads. SpaceX's depot system, by contrast, is dynamic, scalable, and directly optimized for heavy cargo delivery anywhere in the solar system. NASA has recognized the revolutionary potential of this technology, selecting Starship as the human landing system for the Artemis III and IV missions. To land astronauts on the moon, a Starship HLS will first launch to orbit, where it will be refueled by a series of SpaceX tankers before performing the trans-lunar injection burn. This is the ultimate validation of the orbital refueling concept. Here, SpaceX is not just theorizing. They are actively testing this technology in real time. During recent Starship test flights, engineers have begun performing critical in-flight propellant transfer demonstrations. These early tests involve transferring cryogenic liquid between internal header tanks within the ship, gathering invaluable data on fluid behavior under actual orbital microgravity conditions. Behind these historic achievements is an army of world-class aerospace engineers, software developers, and materials scientists. At SpaceX facilities in Boca Chica, Texas, and Hawthorne, California, these teams work in rapid design test iterate loops, building and destroying prototypes to find the optimal solutions to these unprecedented engineering challenges. The risks are undeniably high. A single leak during orbital refueling could lead to a catastrophic explosion, destroying two multi-million-dollar spacecraft and creating a massive field of space debris. The precision required for docking, sealing, and transferring highly volatile cryogenic propellants in the vacuum of space leaves absolutely zero margin for error. To mitigate the risk of space debris, SpaceX's orbital depots and tankers are designed with redundant safety systems. If a transfer is aborted, the ships can quickly isolate their tanks, depressurize the transfer lines, and safely deorbit if necessary. Every component is designed to burn up completely in Earth's atmosphere, ensuring no dangerous debris is left behind in orbit. The choice of materials has evolved significantly. Early designs of Starship used advanced carbon fiber composites. However, SpaceX realized that stainless steel, despite being heavier at room temperature, performs exceptionally well at cryogenic temperatures, becoming stronger and more ductile. It is also far cheaper and easier to manufacture, accelerating the development cycle. Docking two massive spacecraft tail to tail is too complex for human pilots. It requires fully automated docking software powered by real-time LiDAR, optical sensors, and inertial measurement units. The software must calculate complex orbital mechanics, relative velocities, and thruster burns to bring the two ships together with the gentlest possible touch. As fuel is transferred, the ullage gas in the donor tank expands, dropping the pressure. If the pressure drops too low, the liquid will begin to boil violently, creating gas bubbles that can ruin the transfer. To prevent this, the donor tank must be actively pressurized, often using heated gaseous methane or helium to maintain a stable, positive pressure behind the liquid. The seals within the quick disconnects are a masterclass in materials science. Normal rubber or polymer seals would freeze solid and shatter like glass when exposed to cryogenic methane and oxygen. SpaceX uses custom-designed metallic seals and spring-energized Teflon jackets that maintain their flexibility and sealing power even at temperatures near absolute zero. The propellant depot acts as a critical buffer in the orbital logistics chain. Without it, an Explorer Starship would have to wait in orbit for days or weeks as individual tankers launched one by one. This long wait would expose the Explorer to unnecessary thermal stress and risk. With a pre-filled depot, the Explorer docks once, takes its full load, and departs immediately. Low Earth orbit is a thermal roller coaster. Every 90 minutes, the spacecraft transitions from the blazing heat of direct sunlight to the freezing shadow of Earth's eclipse. This rapid thermal cycling creates immense structural expansion and contraction, placing severe stress on the docking interfaces and propellant transfer lines. Managing this stress is a key design requirement. Despite all insulation, some boil-off is inevitable. When gas pressure builds up, it must be vented to prevent the tanks from overpressurizing. But venting gas in space creates thrust, which can push the spacecraft off course. SpaceX uses specialized non-propulsive vents that expel the gas in perfectly balanced opposing directions, neutralizing any unwanted thrust. The Raptor engine itself is designed with orbital refueling in mind. Because it burns methane and oxygen, the engine can be directly integrated into the same fluid networks used for refueling. This unified plumbing design reduces weight and complexity, allowing the engines to draw fuel directly from the main tanks or the smaller insulated header tanks used during landing maneuvers. What SpaceX is building is not just a rocket, it is a transcontinental transportation system for the solar system. The orbital refueling infrastructure is the equivalent of the transcontinental railroad or the interstate highway system. It is the foundational logistics network that will enable all future deep space exploration, scientific discovery, and commercial development. With orbital refueling, the moon becomes easily accessible. Starship can deliver massive quantities of scientific equipment, habitat modules, and life support systems directly to the lunar surface. This will enable the construction of a permanent, sustainable human presence on the moon, allowing us to learn how to live and work on another celestial body before taking the giant leap to Mars. But the ultimate goal has always been Mars. To build a self-sustaining city on the red planet, we must transport millions of tons of cargo and eventually thousands of people. The rocket equation made this a mathematical impossibility. Orbital refueling makes it a matter of engineering and logistics. It is the key that unlocks the door to a multiplanetary future. Critics often raise concerns about the environmental impact of launching so many rockets. However, because Starship burns methane, it can eventually be powered by carbon-neutral synthetic fuels. By capturing carbon dioxide directly from Earth's atmosphere and combining it with hydrogen from water, SpaceX can create a closed-loop sustainable fuel cycle on Earth, just as they will on Mars. Beyond the engineering, SpaceX must navigate a complex web of regulatory approvals. Launching dozens of rockets and storing hundreds of tons of highly volatile cryogenic propellant in orbit requires close coordination with agencies like the FAA and NASA. Ensuring orbital safety, traffic management, and environmental compliance is a continuous, vital part of the program. While SpaceX is leading the charge, they are not alone. Other aerospace companies and international space agencies are beginning to realize that orbital refueling is the only viable path forward. Competitors are starting to develop their own propellant transfer technologies, sparking a new space race that will accelerate humanity's expansion into the cosmos. This technology will also revolutionize space science. Instead of spending billions of dollars to build highly compact, ultra-lightweight space telescopes, scientists can build massive modular observatories that can be launched in pieces and assembled in orbit, refueled, and sent to deep space. The cost of scientific discovery will plummet, opening up new horizons. Ultimately, this is not just about machines, fuel, and mathematics. It is about the human spirit of exploration. It is about our innate desire to push past the horizon, to see what lies beyond the next hill, and to ensure the survival of our species. By conquering the rocket equation, we are ensuring that the light of human consciousness will not be extinguished on a single world. As we look to the near future, the final technical hurdle is the full-scale demonstration of orbital refueling. Over the next few years, SpaceX will conduct dozens of test flights, refining the docking, sealing, and fluid transfer processes. Every successful test brings us one step closer to the first human landing on the moon under the Artemis program, and eventually, the first footprints on Mars. We are standing on the threshold of a new era in human history, an era where space travel is no longer a rare government-funded luxury, but a common, sustainable, and economically viable endeavor. The orbital refueling depots of SpaceX are the quiet, metallic monuments that will mark the beginning of this transition. The solar system is finally within our reach. When future generations look back at this pivotal moment, they will not just remember the size of the rockets or the power of the engines. They will remember the brilliant engineering that allowed us to overcome the physical limits of our home planet. They will remember how we turned low Earth orbit into a stepping stone, and in doing so, became a true multiplanetary civilization. Thank you for joining us on this deep dive into the engineering marvel of orbital refueling. If you enjoyed this episode of Science Aura, please subscribe, leave a comment below with your thoughts on SpaceX's strategy, and share this video with fellow space enthusiasts. I am Dr. Blake, Sachi Vale, and until next time, keep looking to the stars.